A good follow-up to driven motion is a look at series circuits, and while these applications don't seem like they have much in common, it turns out that the differential equation that models the situation is identical between them. The question we're going to look at today is how do we model LRC circuits? First, let's look at what an LRC circuit is. And we've seen this back when we did first-order differential equation. We had some energy source that released some voltage onto a circuit that went through something which we used the letter L for, which stood for the inductor. Then it went through this thing that we used the letter R for, which stood for the resistor. Then we take it through this thing, which we use the letter C for, called the capacitor. And we're not going to worry ourselves with the details of the electric theory. We're just going to model the current and the charge. We said before that I is the current and Q is the charge through this LRC circuit. We also found out that the relationship between the two is that Q prime is equal to I. And when we discussed these circuits back with first-order differential equations, we said that RQ prime plus 1 over CQ would equal E when we had an RC circuit. Or when we had an LR circuit, we would say that LI prime plus RI is equal to the energy flowing through this circuit. Well, if I is equal to Q prime, we can make a substitution here, and that I prime then must be Q double prime, and I must be Q prime. And so if we put them together into one circuit, an LRC circuit, we end up with the differential equation LQ prime prime plus RQ prime plus 1 over CQ is equal to the electric circuit, E. Now, this is the exact same form as the differential equation we saw with driven motion, so we should be very ready to solve this equation once it's set up. Let's do an example. Let's find the charge and current if L is equal to 2 henries. We'll often use H for henries. And R is equal to 12 ohms. We often use omega to represent ohms. And C is equal to 0.0625 farad, or F. And V, the voltage, is equal to 8e to the negative 3t. If the initial charge is equal to 2, and the initial current is equal to 10. Well, we know our equation is L, or 2, times Q prime prime, plus R, which is 12, times Q prime, plus the reciprocal of C, and if we put 1 over 0.0625, we'll end up with 16. Q is equal to the voltage that came out of the battery, which is 8e to the negative 3t. Now we have a higher ordered differential equation that is linear with constant coefficients. We know how to solve these. First, the characteristic equation is 2r squared plus 12r plus 16 equals 0, looking at the homogeneous case. Dividing everything by 2, we get r squared plus 6r plus 8 equals 0. which gives us r plus 4 times r plus 2. So r is equal to negative 4 and negative 2. Which means we know that our complementary solution for Q that satisfies the homogeneous version is C1 e to the negative 4t plus C2 e to the negative 2t. Now we just need to go back and find our particular solution. And we know from our method of undetermined coefficients that our Q particular, based on what our function equals, 8e to the negative 3t, is probably some unknown coefficient times e to the negative 3t. Then Q particular prime is negative 3a e to the negative 3t. And Q particular prime prime is 9a e to the negative 3t. Going back to our original equation, then, we've got 2 of the Q double primes, 12 of the Q primes, and 16 of the regular Q's. So I'm going to multiply by that on both sides. And when I do, I only am going to end up with e to the negative 3t's. So let's organize our terms. We've got 16a, then we've got negative 36a, and then we've got 18a. And when we add those together, it ends up being negative 2a. And we want to have 8 of these e to the negative 3t's, so a must be equal to negative 4. That tells me that Q particular is negative 4 e to the negative 3t. And we know the solution is for Q is the complementary plus the particular, C1 e to the negative 4t plus C2 e to the negative 2t minus 4 e to the negative 3t. But we still need to go back and find our C1 and C2 terms. We can do that by finding the derivative of Q and then plugging in our initial conditions. Remember, the derivative of Q is equal to I, the current. Q is the charge, I is the current. So for our initial values on Q, we have 0, 2, and the initial values on the current, we have 0, 10. But deriving that derivative, I is equal to negative 4 C1 e to the negative 4t minus 2 C2 e to the negative 2t plus 12 e to the negative 3t. Plugging in those initial values, those zeros are nice because all the exponents are going to go to 0, and e to the 0 is 1. So from the first equation, we have 2 equals C1 plus C2 minus 4. And from the second equation, we have 10 equals negative 4 C1 minus 2 C2 plus 12. Scrolling to get some room to solve these, I'm going to move the negative 4 over and the 12 over. So that way my equations become 2 plus 4 is 6 equals C1 plus C2. 10 minus 12 is negative 2 equals negative 4 C1 minus 2 C2. Let's multiply that first equation by 2. That'll give us 12 equals 2C1 plus 2C2. Adding those together gives us 10 equals negative 2C1. Dividing by negative 2, and C1 is equal to negative 5. That first equation was 6 equals C1 plus C2. So adding 5 to both sides, C2 is equal to 11. So now that we have our C1 and C2, we can plug them into our Q equation to find the formula for the charge at any given moment in time on this LRC circuit. Q is equal to C1, which is negative 5 e to the negative 4t plus C2, which is 11, e to the negative 2t, minus 4, e to the negative 3t. The problem also wanted us to find I, which is the current. The current is just the derivative of the charge. So taking the derivative of the function we just found, we get 20 e to the negative 4t minus 22 e to the negative 2t plus 12 e to the negative 3t. And now we've got a formula for both the current and the charge on this LRC circuit at any moment in time. Because the equation is so similar to what we saw with driven motion, there's really not much new here other than changing the context slightly. So now it's your turn to go to the assignment and practice several of these. Good luck.